Howdy folks, Mr. Reed here, and welcome to one more question. So what I'm going to be doing today is actually solving for the intersection point of two graphs, or solving for the solution of an equation that involves a single radical piece, I guess, to it, by, well, using an algebraic method. We could do this graphically too. I don't like doing this graphically by hand, so my suggestion would be if you want to see this graphically, grab something like Desmos, www.desmos.com, try out some graphs there, and see the answers by clicking on the intersection points. It's very nice, and it works pretty well even if your values aren't nice for the solution. If you do a graph by hand, it can be really awkward to try to get estimates of where the intersection points are if they don't fall on very, very nice values. So I would usually advise against that. So if you want to solve for the intersection point of a radical function equal to function, or you're just looking to solve some radical equation, then you're in the right place. We're going to call this one a medium level difficulty, and we're going to get to it. All right, so here we go. I'm going to just take the two functions that are above me right now and just start by setting them equal to each other. So I actually have a nice little transformed radical. If I were to look at the actual transformational form, I'd have to factor out the 2. That would be a horizontal stretch factor of 1/2, and it would be a movement of 5/2 to the right. And then the linear function that's on the right-hand side of my equals is going to have a y-intercept of 4, and it's going to have a slope of -1. So you can kind of visualize what these two things would look like, more or less. But what the important thing for us is that we want to be able to solve for that x value. Now, the way that you're going to be able to do that is by getting rid of the radical, because we have one x that is accessible to us right now, and the other one is trapped forever inside of a radical. Well, not forever, because we're going to get rid of it on this next step. If there was something going on the same side of the equation as the radical, I don't have it set up that way this time. I was going to do that for a spicy one later on. Don't know if I'm going to get to it, but if I do, I'll make it extra awkward and we'll figure it out as we go. But for this one, I want to make sure that it is fairly clear as to what we're doing. But if there was a little piece with it, we would just move it over to the right-hand side with the rest of the linear stuff that's over there. Now, in this particular setup, I'm going to be able to square away the square root in step 1. Now, if we do that, we square the left-hand side, is going to basically get rid of the square root, and we would square the right-hand side, which is going to give me -x times -x, and -x times 4, and 4 times -x, and 4 times 4. So get something like that. This is going to be able to be set up as a nice quadratic, so I have x squared minus 8x minus another 2x when I bring it over for a grand total of minus 10x. And then I would have plus 16, and I'll bring the the other piece of that over, which is add 5 to it, so I'll get 21. So this is actually something that looks like it's nicely factorable. So I'm going to go x minus 3, x minus 7, and we're going to end up with here, oh, I don't need to put that, two solutions, either x is equal to 3 or x is equal to 7. Now, just a little discussion real quick. If I have a radical function that is stretched, I'm not too worried about that, but it's also moved to the right some, it's going to kind of look like this. All right? Now, if I have a linear function that looks like this, how many times does that cut? How many solutions should I be getting? 1. At least with this type of function and this type of line. I mean, technically, if I draw this really poorly, maybe it could do 0. But it's probably not going to be 2, which is what I'm getting right now. The weird thing is we actually are getting the answer for the bottom half of this inverse to a parabola. Now, the reason for that is because way up here, we are discussing the principal root. And if this thing was a negative square root that we had right there, on the next step, when we square it, it still would look the same. So we would basically say negative times negative is a positive. So second line would be the same, no matter if we were doing the underside version or the top side version. So algebraically, it would be identical. So therefore, this should be giving the right answer, whether we have the bottom part of this radical function or square root function or the top part. And so which one of these corresponds to the top part? Well, with my little crummy sketch, you probably could guess that it's 3, but we should really test these values into the original function to see if that actually is the case. So if I put 3 into the original, I'm going to have 2 times 3 is 6, minus 5 is 1, square root of 1 is 1, that's good. Negative 3 plus 4 is 1, that works out well. If I put the 7 in, 2 times 7 minus 5 is 9, square root of 9 is 3, and then is equal to negative 7 plus 4 is negative 3. So 3 is equal to negative 3, that is a no-go. So our answer here is just a 3. So this is how we can solve them algebraically. Sometimes you find extraneous roots and sometimes you don't. Make sure you check your answers back into the beginning setup and you should be good to go. If you found that one helpful, like, subscribe, and as always, take care, folks.